For this week's asynchronous work, we're going to start preparing for what we'll do next week in class. So this is going to look a little bit different than what we did in class this week. If you don't have a calculator handy, you're probably going to want to grab one because we're going to do some calculations today, as we will in class as well. So what we're going to look at today is we're going to focus on this idea of finding greatest common divisors of two numbers. And in class next week, we're going to learn another way of finding greatest common divisors. So we might ask, why do we care about greatest common divisors? And the answer comes in this first question. So if I ask, is this number 17,017 in this group U of 142,477, then we remember that this question is saying, this is another way of asking, is 17, is this number relatively prime to 142,477? Remember, relatively prime just meant, do they have any common factors? So another way of asking this is, do 17,017 and 142,477 have any common factors? And another way of asking this is asking, is the greatest common divisor of these two numbers equal to 1? Okay. The greatest common divisor is the biggest number that divides both of these. So if the biggest number that divides both of those numbers is just 1, then that means they have no common factors besides 1, and every number shares a 1 in common. So that's what we're looking for here. So the question is, how can we compute greatest common divisors or greatest common factors? These phrases mean the same thing. So you might know how to do this already, but let me review this with you. And then in class, we're going to learn a new method, which I suspect you have not learned, although you might have, but probably not. So there's a couple ways that we could find the greatest common divisor of two numbers. So the first way is that we could list all the factors of our two numbers and then select the biggest number that's a factor of both. So let's do this with an example. We'll do this with an example smaller than the one that I had above because that example is going to be a little bit painful to list all the factors. So let's maybe do an example where we're trying to find the greatest common divisor or the greatest common factor if you prefer that phrasing, but I'm always going to say GCD for greatest common divisor. That's what we tend to use in a number theory style class. So what's the greatest common divisor of 18 and 24? You might be able to see this just by looking at it, but humor me and do this example with me. So if I list the factors of 18, what are numbers that divide 18? Well, the number 1 divides 18. The number 2 also divides 18. The number 3 divides 18. 4 does not divide 18. 6 divides 18. We notice that 3 times 6 is 18. So once we've gotten a pair, like a side-by-side pair that divide the number we're looking at, then it actually makes life easier. Now I can just say, what do I multiply 2 by to get 18? That's going to be 9. And then what do I divide 1 by to get 18? That's 18. This will give me all the pairs when I kind of get to that midway point, the point where those two numbers multiply together to give me 18. I know that's the halfway mark. Kind of makes our life a little bit easier. Okay, so these are all the factors of 18. And then we want to do the same thing. What are the factors of 24? So 1, of course, divides 24. 2 divides 24. 3 divides 24. 4 divides 24. 5 does not. 6 does. Ooh, and I notice I've got into the midway point here because 6 times 4 is 24. So now I can just say, okay, these are a pair. What do I multiply 3 by to get 24? That's 8. What do I multiply 2 by to get 24? That's 12. And then what do I multiply 1 by? That's 24. Okay. You could get all these numbers without noticing that like midpoint thing that I was talking about. I just think this is easier. Okay, so now we look at these two lists and we say, what's the biggest number on both of these lists that is in common? So we see that they both share a 1, they both share a 2, they both share a 3, they both share a 6, and that's it. 6 is the biggest number that they have in common. So 6 is the GCD of 18 and 24. Okay. You might notice that this process would take a long time if we had bigger numbers. This is not a process that I would want to try and use for my example above. Okay. So we probably need some better processes, but I think this one's good because this just kind of points out exactly what is the greatest common divisor, the greatest common factor. It's the biggest factor that they both have in common. So another way that we could find the greatest common factor is find the prime factorization of both of our numbers, and then pick the everything that occurs in both of those prime factorizations. Um, Okay. So it might be pretty easy here to factor 18 and 24 into their prime factors. Again, I'll do this like we did in class last time, because this process will be helpful again for bigger numbers. So if I want to factor 18, I just say, what's a number that divides 18? So how about 2 and 9? So 2 times 9 multiplies to give me 18. 2 is prime, so I'm going to highlight it. 9 is not prime, so I'm going to divide it into prime products. So 3 times 3 gives me 9. And 3 and 3 are both prime. So I have gotten down to all prime numbers here. And so 18 has a 2 and then 3 or two threes. Okay, so 18 is 2 times 3 squared. And then if I do the same thing for 24, I can divide this up into, maybe I could multiply it as 4 times 6. Neither of these numbers is prime, so I have to break both of these up. 4 is 2 times 2, and both of those are prime. And then 6 is 2 times 3. Those are both prime as well. So 24 is 2 cubed times 3. Okay. And now I have to ask myself what appears in both of these factorizations. So I notice that I have a single 2 that occurs in both of them. I can only include a single 2 because 18 only has a 1 2. And then I also have a single 3. Again, I can only include a single 3 because 24 has a single 3 in it, doesn't have any more than that. So this means that the GCD of 18 and 24 should be 2 times 3, which is 6. Oh, that's good. We got the same answer that we got using the other method. Okay. The final method that we could use to compute the greatest common divisor of two numbers is something called the Euclidean algorithm. That's what we're going to talk about in class next time. The Euclidean algorithm is nice because it's going to give us a process, an algorithm, that we could put into a computer to find the greatest common divisor that's not going to involve factoring, because remember we said sometimes factoring can be hard. So the Euclidean algorithm will kind of give us this really nice process for finding greatest common divisors. But in the meantime, let's get some practice finding greatest common divisors using prime factorizations because this is instructive, even if it's not going to be our final method. Okay, so we could go ahead and do these examples that I have here. I'm going to erase what I have just so that I have room to write. So again, I would suggest using the second method, find the prime factorization of each of these numbers. And I would suggest you stop the video here and try to do this on your own before you watch me do it. But if I look at part A, if I look at my numbers 16,785, the first thing I notice here when I'm trying to factor this is I notice that it ends in a 5. So it's going to be divisible by 5. So let's go ahead and divide it by 5. Pick things that are easy if you can see them. Anything that ends in an even number would be divisible by 2. So that would be a good place to start in a case like that. So 1, 6, 7, 8, 5 divided by 5. Okay, that's going to give me 3, 3, 5, 7. Okay. And now I have to try and factor that. So let's see what happens here. So I notice this is not going to be divisible by 2 because it does not end in an even number. Also not going to be divisible by 5 because it doesn't end in a number divisible by 5, either 5 or 0. So we could see if it's divisible by 3. The easy way to check if a number is divisible by 3, I think we talked about this in a previous video, is add the digits together. So do 3 plus 5 plus 7, which you can hopefully do in your head. That's 18. 18 is divisible by 3, which is actually going to tell us that my original number is also divisible by 3. So 3357 should be divisible by 3. You also could have typed that into a calculator, which you're eventually going to have to do, but I think it's useful to find these tricks for easily checking if things are divisible by a number. So this is 3 times 1119. 1119, if I add the digits up, I get 1 plus 1 plus 1 is 3, plus 9 is 12. That's also divisible by 3, so this is going to be divisible by 3. And then I get 373. Now I have to decide what happens to 373. We notice that's not divisible by 2 because it's not even. Not divisible by 3 either because the sum of these digits is no longer divisible by 3. Not divisible by 5 because it doesn't end in a 5 or a 0. Notice I'm only checking prime numbers. I don't care if it's divisible by 4 because it's already not divisible by 2. So I'm just checking prime numbers. Okay, so we could keep doing this. We can keep checking to see what prime numbers might divide 373. For instance, if I divide this by 7, not evenly divisible. I had to do that in a calculator. So we could keep going. And we might say, oh my goodness, when can we stop? Do I have to check every number between 2 and 373, every prime number, and see if it's divisible? And this is where we get a nice little trick. If I take the square root of 373, we can do this. 373 square root of that is 19 point something, 19.3. So there's a nice fact that tells me all I have to check is this divisible by the prime numbers that are less than 19.3? If it's not divisible by any of these primes, then it's not going to be divisible by anything. And so it will itself be prime. So the prime numbers less than 19.3, those are 2, 3, 5, 7, 11, 13, 17, and 19. Okay, so these are the only prime numbers that I have to check. If none of these divide 373, then 373 is going to be prime. This is a really nice fact that comes in handy for things like this. So we've already said this is not divisible by 2, 3, 5, or 7. So check and see. Not divisible by 11 either. Not divisible by 13. Not divisible by 17. It's also not divisible by 19. So what that means is that 373 is itself prime. Okay, that's kind of handy. That's not a prime number that I know off the top of my head. I know that Google could tell you that, but again, it's useful to think about how this works because if we wanted to try and program any of this into a computer, we would need to understand how it works and not just be able to Google it. Okay, so my prime factorization then of this number is 3 squared times 5 times 373. Okay, because those were my final factors here. Okay, so now we have this other number to factor. 102,575. Hopefully this will be faster. This one is clearly divisible by 5. It's 5 times 20515. It's divisible by another 5. 5 times 4103. 4103 is not going to be divisible by 3 because the sum of those digits is not divisible or is not divisible by 3. Also not divisible by 2 or 5. So let's maybe try 7. Not divisible by 7. Is it divisible by 11? It is divisible by 11. So it's 11 times 373. Ooh, we found that number 373 again. We already know it's prime, so we're going to stop there. Okay, so we've got our prime factorization here. We have 2 5s, an 11, and a 373. So this is going to be 5 squared times 11 times 373. Okay, and then we ask ourselves, what do these two numbers share in common with their prime factorization? So they have a 5, a single 5 in common, and then they have a 373 in common. So the greatest common divisor of these two numbers will be 5 times 373, which is 1,865. Okay, so I'm gonna let you guys try the other ones on your own, see what you can do there. Um, Maybe I'll give you the final answers to them so you can check your work. And then if you don't get the same answer as I do, you can keep watching the videos. So I got 16 here, and then I got one for the last one. So if you did not get those answers, and hopefully you've paused and tried to do them, then watch along with me as I factor these numbers. Again, like I said, in class, we'll find maybe an easier or at least a more algorithmic way to find these GCDs. But it's instructive to do what we're doing here. So this number I see is going to be divisible by 2 because it's an even number. So if I divide it by 2, I get a 728. That's also divisible by 2. I get 2 times 364. That's divisible by 2 again. 182, that's divisible by 2 again. 2 times 91. Okay, then we have to decide if 91 is going to be prime or not. Um, so it's clearly not divisible by 2, also not divisible by 3 or 5. So let's try dividing it by 7. Oh, it is divisible by 7. It's 7 and 13. Okay, so it looks like how many 2's did we have? 1, 2, 3, 4. So this number is 2 to the fourth times 7 times 13. Okay, and now I have to factor my other number. So 16 or 19568. Again, that's divisible by 2. That leaves me with 9784, which is divisible by 2 again. And we get another divisible by 2. 2 times 2446, which again is divisible by 2. And then we get 1223. Now we have to decide if 1223 is prime or if it has any factors. So let's look, the square root of 1223 is, what is it? Is 34.9. So if I want to decide if 1223 is prime or not, I have to divide it by all the primes less than 34.9. So those primes would be 2, 3, 5, 7. I always think that 9's a prime number, but it's not. So if I ever write 9 down as a prime, you guys should stop me. 11, 13, 17, 19, 23, 29, 31. Those are all the prime numbers, should be all the prime numbers less than 35. So I have to test to see if 1223 is divisible by any of these. It's easily not divisible by 2 or 5. The sum of the digits there, 3 plus 2 plus 2 plus 1, is not divisible by 3. And then just start dividing it by all these other numbers, and you will find out that it's prime. So none of these other numbers divide 1,223. So this number turns out to be prime. Kind of an interesting prime number there. So my prime factors here then are going to be 2 to the fourth times 1223. Okay. And so then what factors do my two numbers share in common? Well, it looks like they share a 2 to the fourth in common. So the greatest common divisor then is going to be 2 to the fourth, which is 16. Okay, one final example, just to get some practice here. So if I'm looking for the factors of 31581, that one's not going to be divisible by 2 or by 5. But if I add the digits, I notice this will be divisible by 3. So I will start by dividing it by 3. And that leaves me with 10527. That turns out to be divisible by 3 as well. That one's no longer divisible by 3. If I start dividing this, it ends up to be divisible by 11. Okay. And then what else? So 319 is, divisible by another 11 and a 29. Sorry, I was about to sneeze. So it looks like this number here is 3 squared times 11 squared times 29. And then my 1820, that's divisible by 2. So I get 2 and 910. 910 is divisible by another 2. And we get 455. This is divisible by 5. Again, if you're dividing this in a different order than I am, then that's okay. 91 turns out to be, it looks prime, but it's actually not. It turns out to be divisible by 7 and 13. So my prime factorization here is 2 squared times 5 times 7 times 13. Okay. Ooh, and this is interesting. We notice that if we look at these two lists, they have nothing in common. If the lists have nothing in common, then the only number that will divide both of these numbers is just a 1. So these two numbers have a GCD of 1. This is the same thing as saying that they're relatively prime. Okay. And so what this would mean is that the smaller number, that 1832, is an element of U31581, because to be in that group, these numbers have to be relatively prime. So lots of fun facts here. In the next video, we'll point out an interesting fact that will be useful for us as we do the Euclidean algorithm.